if you look at topographical maps, this is essentially a contour map where these curves here, these portions of a circle, are essentially level curves. And it's possible, I haven't verified this yet, it's possible that Dürer may have invented the contour map at this point. I'm not sure whether he was predated by anybody else at this point, but this does seem to be a very, very early appearance of these contour maps. And again, you can conceivably see that an artist may want to draw an ellipse, may want to draw hyperbola, may want to draw a parabola. These curves do appear in certain physical contexts. And then Dürer goes on to what we might think about as a purely geometric problem. How do you construct regular polygons? And there's some very interesting observations that Dürer makes. So so we'll start off with the regular hexagon. Again, regular hexagon is very easy to draw. The side of a regular hexagon is equal to the radius of the circle that it's going to be inscribed in. So if you want to make a regular hexagon, you can just, the sensible thing to do is start off with the regular hexagon, and we can make that fairly easily. And if I join the alternate vertices, that's going to give me my regular equilateral triangle. So Dürer is very familiar with this construction. He describes it to the artist. It's a standard geometric construction. What's interesting is that Dürer then goes on to some constructions that are not standard. And the most important one is an approximate construction for the heptagon. And Dürer gives the following construction, which is if I take the equilateral triangle, so take the equilateral triangle in a circle, take half the side of the equilateral triangle, then half that side is, I can use this half side as one side of a heptagon that's inscribed in a circle. And the interesting thing about this is a method that's actually given by Alvin Waffa in that book I referred to earlier, the Parts of Geometry Necessary for Artisans. As nearly as I've been able to tell, this method is new to Europe. In Dürer's book. There is an equivalent method that is described by Heron of Alexandria in the 1st century AD, and is also described in other artwork, in other drawing manuals of the time period. This particular method seems to be new to Europe with Dürer's work. And Kepler, about a century later, has a wonderful comment about this. It's not an exact construction, first of all. It's not an exact construction. And Kepler says, well, it's obviously, if anybody who does this, they're going to find that it's obviously too short of the side. Well, how obvious is that? Well, here's the first hint. It may not be clear there, but there's a regular heptagon also inscribed in that same circle. So that circle shows the heptagon that Dürer you would construct using Dürer's method. There's also a regular heptagon inscribed in that same circle. The difference between the two isn't very obvious. Actually, that difference, let's blow that up a little bit. If you go back, if H is the actual vertex of our regular heptagon and A prime, so go back one step here. So here's our A prime there. If I'm going to build 7 sides around using this BA length here, and that's going to take me to G, and then I join these last 2 sides there. Well, what I'm going to end up with is the approximate heptagon that Dürer constructed is right there. The actual regular heptagon is right there. And just as an idea of how accurate this is, if we take a circle with a diameter of 20 feet, about half the size of this room, the approximate construction gives us a side of 8 feet, 7.92 inches. The actual side of a regular heptagon is about 1/4 of an inch longer. So in a 20-foot circle, you're talking about 1/4 of an inch discrepancy in the sides. So this is Kepler's obviously too short. Okay, well.